This is Thomas's Calculus, 14th edition. From this book, Chapter 11, Parametric Equations and the Polar Coordinate System. If you scroll down, you can find on page 653, Cycloids. We will discuss example 8. We will derive parametric equation of this cycloid. Deriving this parametric equation is not important in my current video. We can draw this cycloid using Mathematica. For example, parametric plot. These are square brackets. From this parametric equation, I would let A to unit 1. Then this is curly brace. T minus sine T. This represents x coordinates. Then 1 minus cosine T. This represents y coordinates. We need curly brace once again. T runs from 0 up to 2 pi. Now shift enter. Then you will see the graph of cycloid as in figure 11.10. If we give 4 pi, then it will plot it like this. Parameterization of a cycloid is not of much problem. The problem is angle conversion from cosine 3 pi over 2 minus t is equal to negative sine t. Sine 3 pi over 2 minus t is equal to negative cosine t. I haven't used my mathematics seriously since 1996 or after since I graduated from my college. So we will learn how to convert cosine angle, sine angles properly. Before we derive parametric equations for cycloid, we will learn shapes and periodicity of trigonometric functions. I got this table from Wikipedia, list of trigonometric identities. If you scroll down, you can find this table, shapes and periodicity of trigonometric functions. As long as you remember identities in this blue box, you can get identities in the red box. We actually don't need to remember identities in this yellow box. Instead, we will learn how to infer or derive these identities quickly and correctly. Here, I draw a unit circle. This is unit circle. This is angle theta. We assume theta is greater than 0. Theta is positive angle. Cosine theta equals x. Sine theta equals Why? Because we use unit circle. From this, we say the sine of cosine theta is the sine of x. From this, the sine of sine theta is that of y. If you remember, the sine of cosine theta is the sine of x. The sine of sine theta is that of y. You will never fail to convert the angles properly. You will never fail angle shift or angle periodicity. This is first quadrant. This is second quadrant. This is third quadrant. This is fourth quadrant. In the first quadrant, x is positive, y is positive. In the second quadrant, x is negative, y is positive. In the third quadrant, x is negative, y is positive. In the fourth quadrant, x is positive, y is negative. We all are familiar with these things. So I will delete these things because we are already familiar. Now cosine phi over 2 n plus minus theta, sine phi over 2 n plus minus theta. How can we infer the identities? We classify n even or odd. A. If n is even, cosine phi over 2 n plus minus theta equals cosine theta. We have to determine the sine. Sine phi over 2 n plus minus theta. If n is even, it is sine theta. We have to determine the sine of this function. B. If n is odd, cosine phi over 2 n plus minus theta equals sine theta. We have to determine the sine. Sine phi over 2 n plus minus theta equals, if n is odd, it becomes cosine theta. We have to determine the sine of this function. Now I scroll. I will copy, paste it here. I will copy this, move it down like this. If this angle is in first quadrant and the fourth quadrant. First quadrant, fourth quadrant. Cosine x follows the sine of x. X is positive. X is positive if in first quadrant or fourth quadrant. So, if n is even, if this angle is in the first quadrant or fourth quadrant, this is positive. If this angle is in second or third quadrant, this becomes negative, like this, because cosine follows the sine of x. In the same manner, if this angle is in the first quadrant and in the second quadrant, this is second quadrant. Sine function follows the sine of y. So, y is positive in the first quadrant and the second quadrant. So, it becomes positive. If we scroll up in the first quadrant, y is positive. In the second quadrant, y is positive. Now, if this angle is in the third quadrant or in the fourth quadrant, y is negative. So, this becomes negative, like this. You have to remember the logic. Now, we scroll up. If n is odd, we will copy. Now, n is odd. If this angle is in first quadrant or fourth quadrant, this is fourth quadrant. Cosine follows the sine of x, so it is positive. If this angle is in second quadrant or third quadrant, x is negative. So this becomes negative. Likewise, n is odd. If this angle is in first quadrant or in the second quadrant, sine follows y, the sine of y. So it becomes positive. If this angle is in third quadrant or in the fourth quadrant, this is fourth quadrant. Y is negative. So this should be negative. We have to remember these things. If you are doubt, please replay this part of the video. This is very, very important. If you apply this reasoning, trigonometric functions are doable. Now I scroll up. We will practice a little bit. For example, in this case, sine phi over 2 times 1 minus theta, n is odd, so it can be cosine theta. We assume theta greater than 0, less than phi over 2. Then this is phi over 2 minus theta. This is theta. This angle is this angle. So this is first quadrant. In the first quadrant, sine follows y. So y is positive. So it is positive. In this case, cosine phi over 2 times 3 minus theta, 3 is odd, so it should be sine theta. We have to determine the sign. This is 3 phi over 2. If we subtract, theta is positive, then this angle falls in third quadrant. Cosine follows x. X is negative in third quadrant, so it becomes minus. This result minus sine theta perfectly matches. For example, in this case, sine 2 pi minus theta, this is periodicity, so sine minus theta. We apply this rule, so it becomes minus sine theta. It matches perfectly. In this episode, we need this identity and this identity. Now scroll down. We will now derive these parametric equations for cycloid. Rolling wheel. This is a wheel. It is rolling. T represents time. This example comes from Thomas's Calculus 14th edition from chapter 11, Parametric Equations and Polar Coordinates. We will discuss parametric equations, then polar coordinates, both in 2D and 3D space. From this chapter, if you scroll down, you can find in page 653, Cycloids, example 8. We are solving this example. Here, t represents time. So, we add at. X equals at plus. This point is at A. So, we have to add this distance, a cosine theta, a cosine theta. I will delete y equals this height is a, or radius of this wheel is a. So a, this height, a plus, I will delete. We need to add this height, a sine theta, a sine theta. It's very simple as specified here. T represents time. Please read this diagram very carefully. This is angle theta plus this is t. Theta plus t sweeps 3 pi over 2. Theta equals 3 pi over 2 minus t. Now we substitute theta in this equation. Then x equals at plus a cosine 3 pi over 2 minus t. T is time, always greater than 0. Now cosine phi over 2 times 3 minus t equals n is odd, so it becomes sine t. We have to determine the sign. Cosine follows the sine of x. This angle is here. We regard t greater than 0 from 3 pi over 2. This angle falls in third quadrant. In third quadrant, x is negative, so it should be negative. That is cosine 3 phi over 2 minus t equals minus sine t. In the same manner, we simplify y like this. Y a plus a sine theta, a plus a sine 3 phi over 2 minus t, sine phi over 2 times 3 minus t equals, this is odd, 3 is odd, so cosine t. This angle is in third quadrant. Sine follows y. The sign of y in third quadrant is negative. So negative. That is sine 3 phi over 2 minus t equals negative cosine t. With this and this, we can say, please notice this equation. X equals AT, this part, then this part, A minus sine t. So AT plus A sine t. Now y equals A plus A minus cosine t minus cosine t. So A minus A cosine t or A t plus sine t A 1 minus cosine t. This is x, this is y. We derived parametric equations for this cycloid, as in this equation. Sorry, I made mistake. This is plus, this is minus. So this is plus, this is minus. I made mistake here. It is minus. It is minus. I made mistake here. We got this result. As I said previously, without parametric equations, we cannot even plot a plain straight line. For example, without parametric equation, we cannot draw y equals a or x equals b on the computer monitor. Without parametric equations, we cannot even draw a straight line.